My name is David, and the upcoming clip is from a debate between MCToon. It's not MCToon. His first name's Michael. The C's made up, and the Toon is his last name. And Gary from Draft Science or Draft Physics. But Gary kind of has some alternate views on how physics works, and I think he doesn't understand how image processing works. And so we're going to watch the clip and see what Gary has to say. It's about gravitational lensing. And just let them talk for a few minutes here.
Welcome everybody to Tuesday night. I'm your host MCToon, and tonight we have a debate. This is going to be a little different than what I usually have. This is with not a flat earther. This is with Gary from Draft Physics. Welcome, Gary.
Thanks. Appreciate it. I want to, thank MCToon for allowing me this opportunity. I really do want my ideas fairly tested. I'm really interested in people who can, in some way, demonstrate that I've made a mistake, or I have it all wrong, or I'm an idiot, or any of that stuff. And just to throw it in there, I'm not a flat earther. Okay. I think regular physics is pretty flat and dull and wrong, but I don't think the Earth is flat.
The first one is gravitational lensing. And here is his presentation on it.
All right, 5 minutes on the subject of whether or not photons, light, is bent twice as much as regular matter by gravity, let alone bent at all. The story starts with the Eddington experiment done to prove Einstein's theory of relativity. And so, as I understand the story, this was mostly all Eddington's idea. And, and he was one of the first defenders of Einstein's theory of relativity. So he went in with a bit of a bias. Now, in his journal, it's just a fact, he states, so you'll have to accept my testimony, all right, I'm not lying about it, because I can't find his journal online anymore, but he states right explicitly in his journal that the weather's terrible, that he got 10% of the data quality. That is, he was expecting going in to get 10,000 stars per glass slide, and he only got 1,000. So a huge degrade in the data quality. It wasn't a 12 noon eclipse. It was something after 1 o'clock. And the weather was horrible. Okay, so it rained a lot. Okay, which means that the seeing was also bad in the worst kind of way, which is a bunch of water molecules in between you and space, which is even worse than just clouds. But anyway. So not the kind of experiment you write a New York Times headline saying Einstein proven right. He said right in his journal, I wouldn't stake my life on these results. That's an absolute fact. All right, so this isn't the kind of experiment that you say, okay, we proved it. And then all the other experiments and eclipses, there was one in 1922, and then, somewhere in the 50s they tried again, and every single one of them was flawed. Now, there was 2 expeditions that went with Eddington, so Eddington had the horrible weather. Unfortunately, the people that went to South America, I think that was South America, they didn't adjust the telescope correctly, so their images weren't too good either. All right, so it didn't go well at all. You're talking about 12-foot-long telescopes dragged up mountaintops. The whole thing seemed a marginal experiment, even in the best conditions, and they had the absolute worst. Now, I'd argue that isn't good science. You don't take an experiment that flawed and make it a foundation for a statement about what's been proven, okay? And then the fact that they could never repeat it, all right, since Eddington, the experiment hasn't been done by a competent telescope, a big one, okay, beyond the margin of error. So it's just not a proven fact by that particular experiment. Now, the best part of the experiment is that it's an optical experiment, so it doesn't rely on scatter. So scatter won't produce image. So the other kind of satellite experiments they've done where they've called it measuring bending, those all include light that does go through the corona of the suns, and light that goes through globular clusters, and light that goes through all kinds of other messes. The whole idea of Eddington was he had to pick a star well outside a diameter of the sun, at least a radius. And I think it was a full diameter. So he had to pick a star that was pretty far from the sun, because there's every expectation that inside of that distance there's plenty of particles to cause scatter, and scatter will create bending in all directions.
Okay, he's saying there's experiments that pass through the corona of the sun. There's been other experiments that didn't rely on the corona of the sun. They generally go around galaxies and dense objects that they pretty much figure are black holes. And also, he will go on into about attacking an amateur astronomer. Amateur astronomers actually have quite good equipment nowadays. They find exoplanets. They find a lot of asteroids and comets and stuff. And this is because they get time to focus on different areas of the sky that, like the big professional telescopes, just don't have time on their schedule for a lot of this stuff. So amateurs can focus on looking for comets in a small patch of the sky, and that's what they do a lot of good research doing that. So attacking an amateur because he's an amateur is just silly. Just astronomy is one of the few fields nowadays that amateurs still do a lot of important research in. Okay, I'm going to let him go back and talk.
So from any place you could see the light, so to speak. So all the radio telescope experiments are disqualified because they're not image experiments. So the experiment really hasn't been repeated. And the fact is there's 400 times better resolution in space. Even in the fact that, look, with all the telescopes, so since 1919, I'm supposed to believe that with all the telescopes on Earth, all the observatories, there hasn't been a single one that had a nice noonish eclipse happen over the top of it. Not one. I'm sort of out of time. Shucks. Anyway, so space is 400 times better resolution. You don't need an eclipse. It's a 5-minute experiment, and it's even more than 400 times when you figure out that most of these eclipses aren't 12 noon eclipses, so it's not ideal conditions. So we're talking about 600 times better resolution from space, and we're supposed to believe it's never interested NASA to bother pointing a GoPro camera at the surface of Jupiter, because the fact is, with 500 times better resolution, you could use the surface of Jupiter. All right, anyway, that's my argument.
Right. So, I'll get mine ready here. That's not it. Just a second. So, I'll have about 5 minutes. I haven't timed it. His was timed, but hopefully it'll be close. And I'm going to share my screen. To share my screen to you, Gary, so you see it. All right, you got that?
I can see that. Yep.
All right. And then I'm going to make sure people can see you. So gravitational lensing, the hypothesis from Newtonian is that photons have a mass energy equivalence. That's the E equals mc squared thing that people have seen about, have heard about. It's a pretty popular thing. So the hypothesis from general relativity is that the light passing near the gravitational well, like the sun, will deflect twice the Newtonian amount. The Newtonian amount is light has mass. The general relativity amount is that space is bent. So here's a quick diagram of what we're seeing. And at the bottom, this is the important part. It's the equation This is not, it looks maybe a little daunting. It's not too bad. That 1/2 times 1 plus gamma part, that 1 is in the parentheses there. That represents Newtonian bending, and gamma represents general relativity bending, which should be 1 if general relativity is correct. So in parentheses, if general relativity is correct, you get a 2. You multiply that by the 1/2, and that whole first pair of terms turns into a 1. So it doesn't affect anything if general relativity is correct. And then you've got the equation there, 4 times the gravitational constant times the mass of the sun. That's the m with that little circle with the dot in the middle. Get your head out of the gutters, boys. And then all that over c squared times d, and d is the distance from the center of the sun in meters. And then all that times 1 plus the cosine of phi over 2. Phi is the angle that the light is coming towards the sun there. So, oh, I had all these nice arrows. I didn't even use them. So there you go. For a grazing ray, so if the light goes right next to the sun, which you couldn't really see in the optical because there'd be too much messing from the corona. You've got phi is 0 because it's like right next to the sun. You've got d. That's the distance from the center of the sun is the radius of the sun. It's right on the edge. And then that d theta, that's the change in the angle. The change of the angle then would be the change in the apparent position. The whole thing then, you solve for all that, you get at the bottom there, d is about equal to 1/2 times 1 plus gamma times 1.7505 arc seconds. So if you ever heard about gravitational lensing near the sun, 1.7505 or 1.75 is the number. That's where it came from. That's how it's derived. It came from Einstein's field equations. I didn't go through that because we don't have 2 hours. So we've got the Newtonian prediction, which is 2 GM, and the Einstein prediction, which is 4 GM, which is twice as much. Here's the graph. This is the easy part to understand. We've got the red line is the hypothesis for Einstein, and the blue is the hypothesis for Newtonian, and then of course 0 is the hypothesis for it doesn't bend at all. The left side of the graph is at 1 solar radii, so it's right at the edge of the sun. And then as you move toward the right, you get farther and farther away, and on the far right of that graph is 6 solar radii away. So that graph is what it's supposed to look like. Red is the hypothesis for general relativity. So here is then Eddington, as he mentioned. This is a copy of one of the plates with the circles of the different stars that they measured. And here is the plot of the stars on that graph. And you can see the black line is the hypothetical Einstein, and the stars there are the blue stars. That is where they were measured to be, the actual displacement of the stars that Eddington measured. So it was a pretty good match to the graph. Now, he had mentioned that it wasn't at noon, and that's fine because here is the actual paper that Eddington wrote. He says the following corrections for differential refraction and aberration are calculated from the times dates of exposure. So they did take into account the effects of refraction in the air and the effects of stellar aberration. So they're controlling for confounding variables pretty nicely. But now Gary said that it wasn't repeated. I don't know why he said that. It's been repeated many times. Here is a list of some of the repetitions of it. 1922, there were 2 papers. 1923, there is a paper. 1950 from the eclipse that was from 3 years prior in Brazil. 1960, 1972, and 1973 was the last one that was during an eclipse until 2017 by Don Bruns, who did a really nice paper right here. Don did a lot of things to take into account he was incredibly precise. He did things to account for the non matching nature of the projection of the field from the camera lens to the flat surface of the sensor. He controlled for, that's this diagram here on the left. He controlled for noise for the filter, for a total black filter, a total white filter. And he did all of the data processing in software here. Here's a couple examples of a little bit how the data looks that they were analyzing. And then let's see, let me get this is a, oh yeah, to get the position of the stars, he used the satellite positioning from the Hipparchus satellite, which is accurate to micro arc seconds. No. Let me go back to this here. So what did that look like? Well, here's there he is in the telescope. It's all computer controlled. There's the samples from his paper, and here are his results. You can see compared to Eddington, it's a much tighter result. So good job there. Now let me show you one more thing here before I move on to this. We have, there's a paper that took all of those eclipse measurements that I mentioned, and have them all together in their deflections in a spreadsheet. Here I plotted all of them, and it matches the Einsteinian prediction. So you can see that scatter chart. It's a pretty fantastic match when you put them all together. But you can see all of these different numbers that were in the data set that I'm looking at here. And if you're interested, I can give you a link, Gary, or anybody, to my work on this. But it's just one of the papers that I cited there.
Published where?
It's on my website, MCToon.net. If you just search for Eddington, you'll find it on that page. But I can
say it wasn't peer reviewed.
No, this is all of the individual papers are, to my knowledge, but it's just a summary of all of the different numbers here. So they took all the different numbers from these different papers here, and then just put them into a paper so that you could have them in do what you want with the data.
I mean, garbage in, garbage out. So I don't have much to say. But I mean, everybody rags and talks about peer review.
Just a second. I'm not done yet.
The amateur experiment wasn't peer reviewed.
I'm not done yet. Just wait.
I'm sorry.
Okay. All right. But it is difficult to do it through the atmosphere using just light, and you have to do it during an eclipse. So there are other much better methods to do it. So here's one. I forgot. Is this by Shapiro, I think? Anyway, here is the optical ones there on the left side. This is a graph by year. And then you have radio telescopes there in the center part. That's either blue or purple, I think. And then you've got VLBI, the very long baseline interferometry, which I'll talk about in a second. And you see the red one is the Hipparchus satellite. So there's 1973 Australia one and 1974 radio interferometry of two quasars. Now the cool thing about quasars is they're not optical; they're in the radio frequency. So our sun that doesn't output much in that radio frequency doesn't interfere. So you can do it during the daytime even, and you can get right up next to the sun because the corona doesn't output the same frequencies. So it's a fantastic way to do it.
Sorry, no chance.
So here's the satellites they use, two of these. And because of their distance from each other, they take and they do interferometry between them and the interference pattern between timing of receiving the signals to get the deflection. So there it is. There's Shapiro is one of the ones on this paper. Again, this is on my website. Just search for Eddington. You'll find it because these are applications of Eddington. So this is a summary of all of several different VLBI measurements, and here is the quantity, this big bell chart in the middle is not anything. What it is showing the numbers of star deflections that were measured based on how close they are to the sun. And the cool thing is that these are precise enough that they can actually get the deflection at almost at like 179 degrees away from the sun. So basically the opposite direction of the sun. The amount of gravitational lensing predicted by Einstein is within the margin of error of the measurements. And so that line on that goes from top left down to the bottom right, that is the measurement of the deflection. And you see it approaches zero over on the right side. And here is the conclusion from that particular one, the Eddington-Robinson parameter. That's GR equals 1. Again, that's in that graph on the formula on the bottom. But the conclusion of that particular study, again, that's on the page there in the lower right, our estimate of gamma is 0.9998 plus or minus 0.0004 is within one standard deviation of the value predicted by general relativity. So, and there again is the chart. So we have multiple ways of measuring that. I didn't mention Hipparcos satellite. They've done it from space too. This was a little bit tailored to go for a flatty who just denies everything that orbits the Earth. So, okay, that is. I hope it didn't go too much over. I think I did a little bit much, but okay. All right, yeah, go. So now we'll have a open conversation here.
Okay, I don't know whether I'm visible or not.
You are. Yep, I just fixed it.
Right.
You can.
Yeah, that's all fine and good. I mean, I've read the papers, so I am aware of the previous eclipse experiments, and one of them was actually a 3 o'clock in the afternoon eclipse. And the guys who wrote the paper, they admitted it's 3 o'clock. It's really lousy seeing, and so we can't say this is outside the margin of error. So from everything I read of those papers, they all had defects of this type. They had some kind
what was the margin of error?
I can't. They just said it was outside the margin of error. So whatever it was, plus or minus 5, they were at some number 7 or whatever. So I'm just saying they couldn't guarantee the results because it was outside the margin of error.
I'm gonna need to see better than that, and why.
I need to see the same thing. Okay, you can show me their analysis and their conclusion. What I want to see is the actual images they measured, and what the amateur didn't provide those. None of these documents provide any of that information. And so what I said in my video, I stand by. Eddington said in his own journal, it's 10% of the data quality, an incredibly difficult experiment under the best conditions. He got 10% of the data quality. Stated in his journal, I wouldn't stake my life on these results. And that experiment got Einstein a New York Times headline. And I'm saying every other experiment they did after that had all these flaws. It's never been done by an observatory, okay? And frankly, it's not been done from space. This particular experiment hasn't been done from space.
Hipparcos did it from space.
No, they didn't. They didn't use a telescope and take images of stars or anything else outside the corona of the sun. It hasn't been done.
So you just nuh-uh on that then?
Excuse me?
Just nuh-uh. That's it.
I'm not saying I'm saying with a particular argument. If I came to you with evidence saying something that you didn't agree with, and I admitted it's 10% of the data quality, and I admitted I wouldn't stake my life on the results, I don't think you would take me too seriously.
Yeah. I mean, no, but my point is Hipparcos has done it from space.
All right, so I don't know. I don't have every detail of every name of a satellite. I'm just saying that I have researched them. So Hipparcos was an image. They took optical images of a sun behind or moving towards our sun.
Yeah, a star. Yeah.
Okay, so they visually looked at it with a telescope.
Hipparcos isn't a telescope like on an observatory.
I'm saying it's
But-
in an image. Well, see, as I tried to point out in the thing, it's in.
Okay. One thing they discuss is gravitational lensing, and where they have, Gary claims, well, there's only 4 photons from this galaxy. From a galaxy, you get a lot more than 4 photons. And what the gravitational lensing does is take one photon that's going one way and another that goes another way and kinds of bends it in space so there are two at the same point, like a lens and a telescope, or a camera works. Like this one. This is a Nikon L320 Coolpix. Gary actually made a subsequent another video about how MCToon was selling him a webcam I'm calling MCToon. MCToon starts talking about the P9000. The P9000 is like it's from the same company, Nikon, and it has like the removable lens and a bigger sensor to it, and a lot of flat earthers use it, but all of them actually use what they think is CGI. They use like a chip on down in here. It's the first version of it was called a CCD, a charge coupled device. And what would happen is a photon would come in and hit the chip and release an electron. What they describe it as a well, when this well got full of electrons, it would move down the chip and give you a pixel. But the thing is, it only gives you black and white images. To combine the images, to get a color image, you have to combine multiple images together. And most chips now has a grid of little tiny filters on top of it. One for green, one for red, one for blue, and one clear. And they make a grid, and there's processing inside your camera that makes a color picture. And before this, they have to put filters on telescopes, and they still do this because it's a better way of processing the image for astronomy. What they do is make a color diagram, which they compare the brightness of the images in different color ranges, so they can tell where the peak of the light is coming from. Just one moment, please. And but also for a lot of images, they do what is called stacking. They take a number of images and stack it, because you may get like one photon hits one little cell or one little pixel on the chip in a certain amount of time. But if you take a number of these images together, then stack them, you get like 10 photons over 10 different exposures. And a lot of the Hubble images, there's one famous called the Hubble Deep Field, where they take 342 images taken over 10 days in the December of 1995, between the 18th and 28th of December, and they combine it together to make one image of a bunch of galaxies. And another thing Gary doesn't understand is the galaxies are compared to the size of the sky, the galaxies are fairly small. The Hubble Deep Field, for example, that has probably hundreds of galaxies in it, is about the same size as if you take a tennis ball and hold it 100 meters away. So it's a very tiny part in the image. And a closer object will take up about the same size as the sky. That's why so you have a galaxy up behind it, and the light comes around. It can magnify the light, and the closer object covers more of the sky, so it takes light from the far sides and collects it better. But I don't know if this is clear, but this is what a lot of people in this kind of space don't get, is that a lot of these images are combinations automatically, even if in your P1000s or P950s, because it just helps to get color pictures. But a lot of times they go, well, this guy is enhancing the image. Yes, a lot of images in astronomy are enhanced to make them look better. The certain colors are made brighter than others and stuff. So that's but the scientists don't actually get the information from a lot of the images that you see in magazines and stuff. They take the raw data. Some of it's like for the Crab Nebula, they'll take a measurement of how big it appears in the sky, and it's slowly growing bigger and bigger, so they can reverse the process and make it smaller and trace back to when it happened about 1,000 years ago. A lot of it's spectroscopy, where they split the light up in a prism or diffraction grating and get a spectrum of the light. So the image that you see in magazines or on the internet are enhanced to make them look more better, and sometimes it does help pick out little weird regions in nebula and in the stars, but it's not the only light that the astronomers are using to determine what's going on. Okay, what was it? Can't think of any other point at the moment, but that's the general issue I had with this bit with Gary. He doesn't get kinetic energy at all, but the entire debate took about 4.5 hours. I shouldn't be watching that long of a debate. There's other things to do, but the Hipparchus. I think they mentioned Hipparchus. Hipparchus was a satellite that measured the positions of the stars. I actually got to use an image one time from Hipparchus for a project measuring P Cygni, which is a variable star in Cygnus. I worked with a professor for one summer where he was studying the images from Hipparchus. You get actually black and white images because it's what they call a Schmidt-Cassegrain telescope. It's basically a reflector. It has a big mirror in the back, and then which reflects the light to a small mirror near the front, and there's a small plastic plate or glass plate to keep the small mirror there, and it reflects light back to a small pinhole. Nowadays, what they use is a Muscatov Cassegrain, which has the plates curved. But the Hipparchus data, what I was supposed to do was measure the positions of the stars, and I forgot to write down the process that I did it, and I forgot to convert to radians, which is compensates for the curve in the space in space. But that was my bad. It took me about and a couple of days later I realized where I made my mistake. But that was kind of a wasted day. But the thing, he was in a rush because I think he was trying to get this data out before our conference in July, and this was in June, so that happened. But so it's just an optical telescope that was measuring the positions of the sky. Now they have a satellite called Gaia, which is out in the L2 position, basically the same position as the James Webb Space Telescope. It's tracking like 1 billion stars. That sounds like a lot, but the galaxy's about 300 to 400 billion stars. So it's just the stars in our local area, plus about 100,000 asteroids. And it's basically doing the same thing, tracking the stars and finding the positions and the movement of the stars. Okay, I think that's my points for this, and have a good night. Hit the like button if you want to, and have a good night.